So with that, I'd like to introduce our keynote speaker, Nikola Stikov. Dr. Nikola Stikov is an associate professor of biomedical engineering and a researcher at the Montreal Heart Institute and co-director of NeuroPoly, the Neuroimaging Research Laboratory at École Polytechnique. His research covers many areas of quantitative magnetic resonance imaging. And Dr. Stikov is a vocal open science advocate, a member of the steering committee of Canadian Open Neuroscience Platform, and co-founder of Neurolibre.org, a preprint server for hosting executable research objects. I'm pleased to hand the floor over to Dr. Stikov so he can speak about what the future of qMRI holds.
Great. Chris, thank you for that kind introduction. And I want to thank all of you for putting this conference together. And also all of you that stuck around for the last day. Usually these conferences have a sharp drop-off in attendance, especially when they're online. But this is Friday afternoon, evening in many places of the world, and yet I'm speaking to about 60, 70 dedicated researchers. So I'm really, really happy to be here. And I have to say, you kind of made my week just having me think about this, because it's a different kind of talk, right? And I hope that I have some interesting content. Hopefully, I won't run too much over time. I realize there's one more presentation afterwards, but I would love to hear your thoughts and hopefully discuss a bit about the future of qMRI research. So just a little bit about me. I did my studies, undergrad, master's, Ph.D. at Stanford, and this is the lab where I finished my Ph.D. at the Magnetic Resonance Systems Research Laboratory, founded by Al Makovsky, and this is all the PIs, or many of the PIs who came out of this lab joining for his 90th birthday. In the back, you will see John Pauly, my PhD supervisor. Here is me with my family, and this is Miki Lustig, whom you'll hear a little bit about in a bit. And this is a presentation without equations, except for one, which is that in MRI, the signal-to-noise ratio is proportional to the square root of the time you spend imaging. And I will use this as a metaphor because I tend to take my time. I took my time with my PhD. I took the time with my presentation today. And I try to take my time when I mentor students and guide them through research. So let me just share my publishing timeline really quickly. This is the very first article that I ever published. And it was actually published a year after I finished my PhD. I never published an article during my PhD studies. And it was kind of like a pre-registration for a study that we did at the Neuro, at the MNI, together with Jennifer Campbell and lots of people that are on this call. So it's really good to see you all here. And this was kind of conducting an experiment that we proposed to do 4 years earlier. And then we shared the data and the code associated with that experiment. And then about 7 years later, we wrote a wrap-up review article that talked about the promise and pitfalls of G-ratio imaging with MRI. Now, if you ask me, even this is too many papers. I would have said this should be just one paper. It should be a pre-registration, an experiment, data and code wrapped up by narrative about where we got. But, at some point I had to compromise because I had to get a faculty position and get tenure. So yeah, I still don't publish a lot, but probably more than I wish. And this is going to segue into the first part of this talk. So I basically structured this as a talk in general about reproducibility, then a talk about qMRI variability, then a solution that I think is essential for qMRI, which is vendor neutrality, and finally talk a little bit about community, time allowing. We'll see how everything goes. So what can I say about reproducibility? Well, let me start with this survey that we conducted on the members of the Reproducible Research Study Group of the ISMRM, the International Society for Magnetic Resonance. Now, it is kind of a self-selective group. So 3/4 of them said, yes, there is a reproducibility problem in our area of expertise. And then another quarter said, maybe. There was probably 1 or 2 people that said, no, there isn't a problem. But I think what's very illustrative is the responses on what are the common problems that you encounter related to reproducibility. And here people said, general lack of detail, no code available, systems being too different between sites, and data not available. Now, our lab has thought very hard about these issues, and we've actually written a couple of editorials in the journal Magnetic Resonance in Medicine, arguing that reproducibility is essential for the future of MRI research. And in this talk, I kind of adapted the title of this editorial into the future of qMRI research. Just a quotation that I would like you to read. Basically, for a truly international journal like MRM, it will be difficult to find a one-size-fits-all answer. However, few would disagree that reproducibility accelerates scientific progress, as well as its translation to clinical practice. As tectonic technological changes shape research in the 21st century, we need to be careful not to damage its foundations, and instead focus on aspects of open science where we can reach consensus. The open science movement needs to pick its battles, and the battle for reproducible research is one that it cannot afford to lose. So this was published in the summer of 2019, just a couple of months before the pandemic. And now there's been another editorial that was led by Mathieu Boudreau, who is a software developer in our lab at NeuroPoly, who analyzed the open source landscape of the journal Magnetic Resonance in Medicine and noticed some trends. Now, you might say that these coincide with the editorial, maybe the editorial helped, but you will see that the percentage of total papers that shared code or data has been rising from 2019 to 2021. It's also because the requirements of the journal now have an offer or an invitation for people to submit data. It's not a mandate. But I think that this is very encouraging. Now, when you see it in the scope of 3 years, you're like, oh, from 2019 to 2021, numbers have doubled. Isn't that exponential progress? But this is the point where I want to give credit to one article in particular, and that would be this one, published in 2007 by Nikola Stikov, that I just showed you in that picture, which is the most cited article in the history of the journal MRM. Over 4,000 citations as counted by Wiley, 7,000 as counted by Google. This is an article that Mickey wrote in his third or maybe fourth year of his PhD. He hadn't written an article before. But the paper came out, and it came out together with data, came out together with code, and it came out with a lot of outreach aspects that I think are interesting, and I'll show them to you just to convince you. But basically, I think this is what made this work groundbreaking. And back in 2007, I thought, well, this is going to encourage people to share everything, because look how successful this paper has been. And yet 2007 to 2021, it's been a slow growth. And sometimes, it just takes time for these things to catch up. Now, this article is very near and dear to me, in part because it might be my biggest contribution to science, because I have a footnote in it. I actually read a lot of versions of it until Mickey finally published it. And I just saw how painstaking the work was. And if my biggest contribution to MRI is a footnote in this article, so be it. There's actually a great movie related to a very similar story. It's Israeli. I encourage you to take a look at it. It's a lot of fun. Now, let me backtrack more. 2007, isn't it slow? Well, this is David Donahoe. He's actually the third author on this article. And he wrote this in 2010, an invitation to reproducible computational research. And he refers to John Clairbout, more than 15 years ago, who began practicing reproducible computational science. And he says, look back to 1992. And here's something that we wrote. An article about computational result is advertising, not scholarship. The actual scholarship is the full software environment, code and data that produced the result. So everybody thought in the 90s that we're going to get here. And yet here we are in 2021, 30 years later, publishing something that looks like this. This is another editorial we wrote. Elizabeth Dupré took the lead. Lots of other people from Montreal contributed. Beyond advertising, new infrastructures for publishing integrated research objects. And just so you don't think that these are just editorials, we talk the talk, but we don't walk the walk, we actually try to make a preprint server available for these reproducible research objects, because I really think they're the future of computational science, and qMRI is computational science. So I wanted to start this way before I get to quantitative MRI, because I feel that this is the community that can contribute to extending this vision of David Donahoe, Buck Haidt, Clairbout, Mickey Lustig, and then a lot of people who are working on reproducibility in this community. So now let me get to the qMRI variability part. And I've always been told that I do tend to have this kind of negative outlook on things, but I assure you that this is kind of work that brings me joy. And if anything, I was really, really happy to be putting these slides together, and I hope you'll see why. So this is a slide from my from my most important presentation I've ever done, my PhD defense, and I've been using it ever since, where I argue that the difference between conventional and quantitative MRI is that in conventional MRI, you have these spoonfuls from an alphabet soup of contrast mechanisms, some T1, T2, some magnetization transfer. And here you are, you get a T1 weighted image, but each of these other contrast mechanisms contributes. And quantitative MRI is kind of like a Japanese bento box. Each of the contrast mechanisms are nicely compartmentalized, and you can take one compartment and you can display it. It will have units. It's going to be a digital image, but not only is it going to be a digital image, it's going to have numbers that correspond to physical quantities. And in this case, that would be the T1 parameter, which is a fundamental parameter. We'll hear about it in the presentation that comes after mine. And I usually use T1 mapping to illustrate how difficult qMRI is, but I will let the next speaker talk about it, and then maybe we can discuss a little bit about in the discussion, because if we can't get T1 right, what hope is there for the other quantities out there that have been around for a little less? Now, this is a video that we made in the pandemic. I'll just start it. It's very short, and it's going to get me to what I think is the most fundamental problem for reproducibility in quantitative MRI.
Well, this is the story that I like to tell to convince people that quantitative MRI is useful. But I do have some confessions to make. In reality, that beautiful bento box that you saw, well, it's actually a black box. And looking at such a black box is not very easy. Now, if only vendors would join forces on a common platform to help us peek inside the black bento box. The compartments are still there, but it's going to be difficult to see them. And hopefully, we can develop some techniques that will get us to agree. Unfortunately, such a platform doesn't exist. And as far as the vendors are concerned, that was just a green screen, and we are left in the dark.
Now, I had fun doing this with my kids, and I hope you enjoyed it. But it drives this point that the MRI scanner is a black box, and it is not a measurement device. Now, if you don't trust my words, I can just show you a screenshot from a manual for a Siemens magnetome that says the magnetome is not a measurement device as defined by the medical product guidelines. Measured values obtained are for informational purposes and cannot be used only as the basis for diagnosis. And we really need to be aware of this. There's historical reasons for it. I can go into them. It actually has to do with the original MRI patents by Damadian and how GE circumvented them. But in reality, we're stuck with something that was not meant to give numbers. If anything, scanners were discouraged from giving numbers. And yet here we are modeling qMRI and feeding this data into AI algorithms, where of course they treat the MRI as measurements. So I think we need to be very aware of this. But every time I try to explain it with MRI context, people's eyes glaze over. So this is what I'm going to do. I'm going to draw analogies with phones and how we're using them and what they were intentionally meant to do initially. Phones are not character recognition devices. So imagine that I start with something that is a comic drawn by Mickey Lustig to explain compressed sensing. This is Mickey. His hair is not as curly anymore. This is John, our PhD supervisor, taking these peaks from a spectrum that's very noisy. And this is another one of those outreach things that Mickey did to make that paper a success. Now, there's images here, and there's also text. And I would like to argue that this is kind of what quantitative MRI tries to do. There's the image, but there's also certain biophysical information that is encoded. So what the MRI scanner does is it encodes both the image and the biophysical properties, but it encodes it in a way that's really difficult to translate. So imagine that I tried to use my phone to actually encode this and encode it in French. Here it is. The pictures are kind of the same. And the language in French, it's automatic. This is done by Google Translate. It's actually not bad. And then here it is done by Apple. And you'll see that it's slightly different. Apple will, just recognize that, yeah, we're talking about the threshold, seuil. It will know that there's something about the signal and the noise. This is actually translated very well. This is translated very well. C'était facile. That was easy. Apple did this weird thing. It said sans it, whatever that means. And yet, when I tried to do the transcription back to the ground truth, back to English, let me show you the result. Yep, just a threshold, says Google. Let's get out of here before someone us sees. It was easy. It is léger. Scarcity does. It's easy to separate signals from noise. And then somehow Apple knows that this garbage translates back into it's light in English. But Apple also sees some words here and gives me Cyrillic and gives me all kinds of other things that were not in the ground truth. Now, I hope that illustrates the issue that we have with different vendors doing things differently. So I asked two Francophone speakers in our lab, Nadia Blostein and Mathieu Boudreau, to actually translate this into French with the same font and to translate it to French that actually makes sense. And here it is in the middle and on the right. And both of these are slightly different, but they are written in the same font, and they do get the message across in a way that's intelligent. They actually knew what they were writing about. And then we did a translation, again, autonomous, kind of post-processing. And in this case, you will see that it makes more sense. You know, everything is kind of understandable. It was easy. It's light too. Yes, we only apply the threshold with just a threshold. Let's get out of here before someone spot us. And, you know, this part here about sparsity, that one's difficult, but you get the point. Something that was put on a common platform, common font, intelligent French language, somehow made for a better translation of the parameters that we're trying to measure. But it took some repurposing of the phone to do this. And, you know, we played with a lot of things. We played with handwriting. You know, I could go and, you know, talk about this a lot, but I hope it gets this point across that MRI were not meant to do quantitative MRI, just like phones were not meant to translate images. And as a result, we have an issue that we're trying to address. Now, talking about variability in quantitative MRI, this is an article that we wrote. It's a meta-analysis about quantitative MRI measurements of myelin. And it's published in eLife. So eLife is one of my favorite journals at the moment. But eLife actually hyperlinks to NeuroLibre and says, if you want to get the data and all of the analysis that came into generating this meta-analysis, you can go there. Now, this is published, and it's not just spreadsheets in a PDF. They're actually interactive plots where you can take a look at different papers, what they imaged according to body type, according to disease, according to MRI modality used. And the conclusion of the meta-analysis, which you can see in this interactive figure, you can see the code that generated the figure, is the following. The correlations between quantitative MRI modalities and myelin from histology are all over the place. Now, there are these tree maps that we can show. Time is tight, but I just want you to appreciate that at the bottom, we have lots of qMRI modalities. At the top, we have the correlations with histology as R squared. You could argue that magnetization transfer, there's inhomogeneous magnetization transfer. T1 and myelin water fraction are kind of better than the rest, but many of these are statistically interchangeable in relation to the underlying histology. And we actually work with Tom Nichols to make sure that we can make this statement, that a lot of these measurements are statistically indistinguishable from each other, which is why the literature does not suggest a universal MRI-based measure of myelin. And informing future studies is difficult due to large prediction intervals. I think this is important to take away. We pick our poison. Each of these techniques has its problems. Some have a lot of parameters. Some are fast but are not myelin specific. And in the end, we need to be aware that everybody's going to have to make some compromises using qMRI and the current concept to measure myelin or any other kind of biophysical property. But I do think there is a way forward, and I will argue that that is just making vendors aware that we need to create comparable MRI. Just like those comics eventually became comparable, not identical, this is what we need to do with the way that we acquire MRI data. Now, we developed software. It's called qMR Lab. Our vision is quantitative MRI under one umbrella. The website is qmrlab.org. It has a lot of tutorials, a lot of different kinds of routines. These are the people that started working on it. Very happy to see even Tommy joining in. He was my first PhD student. And a lot of these people are still working with us. And we published an article. It's not a PDF. It's basically a very short text with a lot of documentation that helps people use different kinds of qMRI routines. So rather than prescribe one way of doing myelin or one way of doing T1 mapping, we just tell people, pick your poison. We support it. Lots of contributors are giving their code here. And I think it's a good way for creating something that I would like to see evolve into an app store for quantitative MRI. But how do we get that on a scanner? Because this is open source, but there is a proprietary barrier. And this is where we're fortunate to be working with a company called HeartVista. Comes from Stanford. Juan and Bill did their PhD in the same lab that I showed you. Bob is a cardiologist. John is my PhD supervisor, and he's on the board of the company. And they create a product called RT-Hawk that basically bypasses anything proprietary in Siemens and GE systems. It is FDA approved for cardiac applications, and it is really easy to deploy any kind of MRI or quantitative MRI sequence via this interface. How does it look in practice? This is our scanner at the Montreal Heart Institute. This is Aga Karakuzu, who's leading this project. And basically, here's a 3T Siemens Skyra, on which we have connected RT-Hawk, bypassing the proprietary pulse sequences of Siemens, deploying our own qMR lab-driven pulse sequence, and then doing the post-processing right there in an integrated workflow. This work we published in MRM just this year. Here's the article. It won a lot of awards at the ISMRM meeting, so that's very encouraging. Both the Reproducible Research Study Group and the White Matter Study Group gave it first place. Aga is available on Twitter, and you should reach out to him. It's always nice to get him to explain his work. And this is actually the execution of the workflows that will explain how we got these results. Everything is containerized, everything is data-driven. And just yesterday, the Neuro actually announced its Open Science Prizes, and Aga was one of the winners. We tried to count, and I think this is his 16th award or recognition in the 5 years that he's been with us. So I think that has to count for something. I really hope that somebody's hiring and gives Aga a good job. And currently he's still doing a postdoc in the lab, and it's really, really good to still have him on board. What did he do? Well, he developed a sequence that is open source, that's hosted on GitHub. Anybody can fork it. The analysis is available. And basically this sequence is deployed on 3 scanners, 1 GE, 1 and 2 Siemens. And what we do is we acquire quantitative MRI maps, both from the Siemens and the GE ecosystems. But then we also apply quantitative MRI maps using this vendor-neutral approach, that is RT-Hawk, and then we compare the results. So there's qMR Lab that processes the results, but there's also qMR PulseSeq that actually does the pulse sequence programming, and there's qMR Flow that orchestrates all of the analysis to remove all the variability that is inherent in doing a lot of these processes manually. The first result is in a phantom, and you will see that GE and Siemens, those are the cold colors, are overestimating these squares that represent the ground truth values of the ISMRM NIST phantom. And then Venus is our vendor-neutral package. Those are the warm colors, red, orange, and yellow. They're really on top of these squares in a phantom for biologically relevant ranges for healthy brain at 3 Tesla for the T1 values. Now that's encouraging in phantoms, but what happens in vivo? So we acquired 3 subjects, and on each of those 3 subjects, we acquired T1 maps, magnetization transfer ratio maps, and MT-SAT. You heard about some of these during the talks these past 3 days. And what you will see just visually, the native implementations, there is a difference between GE and Siemens. And if we're talking about quantitative MRI, this is a problem. If we're dealing with a number, the variability is high. And I'm happy to show variabilities in T1 in other papers, but no time, so let's just stick with this. I hope visually it's convincing. And then with our vendor native approach, the maps become much more similar. Now this is visually, so take some time to take a look at the bottom row. Hopefully you all agree that things are brought closer together. The statistics is very involved, but I'll just go with coefficient of variance, even though I know that Aga doesn't like it, but we don't have time to go into shift function analysis and all the other things that prove that variability has gone down. But for one subject, the variability for coefficient of variance for T1, MTR, and MT-SAT went down by a factor of 3. It generalizes across the 3 patients we acquired, and when we average, we notice that, yes, the variability does go down. Moreover, we try to standardize everything so that we're working with a common data standard, which is BIDS, the Brain Imaging Database Structure, and we're trying to integrate all of these tools into the qMRI lab ecosystem so that we can do qMRI with 1 line of code which really is this line, qMR fit bids wherever the data resides. Now, part of the variability that is removed is because of the vendor neutral approach. Part of it is just orchestrating these things in a way that removes variability between operators, between software versions, between platforms, computer versions. And this leads me to a very influential book. It's not really a book, it's more like an essay, a manifesto called The Cathedral and the Bazaar by Eric Raymond, that talks about how the Linux ecosystem evolved. And there's something that is written there called the Linus's Law, which is given enough eyeballs, all bugs are shallow. I feel that this approach should be incorporated in a lot of things we do in quantitative MRI. And our vision is to go from these vendor-controlled cathedrals to something that would be an MRI bazaar. And this is the proposal. We're calling it MRI Fair. It's a vendor-neutral app store. Might get renamed to MR Bazaar. I actually like the sound of it, but seems like, at least in French, bazaar has different connotations. So we're sticking with something that is a little bit more Western. But it also applies to FAIR principles about things being findable, accessible, interoperable, and reproducible. And it's wrapping to about 25 minutes. So I'll go very quickly on what we do on the community front. We publish a magazine, MRM Highlights, started out as a blog. Matthew Boudreau is still running it. We're promoting reproducible research as interviews with people who are practicing reproducible research in the journal. ISMRM is happening in Toronto. We might organize a satellite event in Montreal. So I would love to see many of you here and hopefully encourage you to practice reproducible research. On Twitter, there's a hashtag about reproducible research insights. All of these researchers share their tips and tricks for producing reproducible research. We organized a hackathon in 2019. We called it the MR-athon, and we hope to do another one this year, next year, 2023, right before ISMRM. I hope you can join us. And this is our vision for what MRI should be. Currently, it's a hurdle race where we jump over data acquisition, data pre-processing, analysis, and finally we publish the work. We'd like to make it more of a sprint, where we start with vendors, we work with vendor-neutral implementations, open source software, and finally publish through NeuroLibre and all of these tools that the Canadian Open Neuroscience Platform is developing. So I would like to thank my lab. The picture is a little bit old, but one of these days we'll get together and do a new one. But you will see a couple of people who are still on this call. And the name of our lab is NeuroPoly. We are hiring. So if anybody wants to have fun and take their time with their research, I encourage you to work on reproducibility with us. Thank you for your attention, and I'm happy to answer questions.
Thank you so much for that great talk. There's a lot of challenges here that I think people aren't aware of until they encounter them in their own work. So is there any questions, Orly?
Yes, actually, I have one. Very interesting talk, by the way. So from Zhao Gong, what do you think about the possibility of the dangers of monopoly? That is, if a single platform becomes widespread, a single error will propagate through the community's research. Open source is great, but a single integrated platform could also bring in problem.
So, I mean, if you look at the numbers, you might say that a monopoly kind of exists. You know, like there is one major vendor, but let me answer it from the perspective of qMRI. They have no monopoly on qMRI because honestly, they don't care about it that much. Liver, cardiac, there's some applications. They're pretty broken, by the way. Like if anybody wants to do cardiac MRI, quantitative MRI in cardiac, don't. I published the preprint. The reviewers thought it was the worst paper ever. Like it actually got a 1 out of 5 on every single category. And I think the reason is because I just wanted to show that we have a problem. So I think vendors need to be motivated to start doing this. And if Siemens says, you know what, all of our scanners are going to have the same kinds of routines, the same kind of post-processing, that might actually be a good solution. But believe me, they won't go there. So I think the problem that we're going to have is actually convince them that, you know, we're not taking a lot of your money because you're not making money off of quantitative MRI. Can you please let us do it in a way that is vendor neutral? And then we have this idea of Android and iPhone both have an app store. You could use iMessage if you want, but you could also use Viber, and Viber will deliver to any platform that hosts it. So in a way, the monopoly here is not something I'm worried about. If anything, it might be good in a very kind of perverted way. It's more that vendors don't care about this. So just raising awareness that you have an issue and you could be opening up yourself to a new market if you let vendor neutral platform do their thing is a good way to approach it. Because I really believe that quantitative MRI without vendor neutrality, without peeking into the black boxes is not possible. It's too noisy. And that's the direction in which we're taking all of this.
Thank you. We have another question from Conrad, who asks, how cooperative have vendors been with this idea?
So I would say surprisingly cooperative. And again, I don't know if it's just kind of, do your thing, or if they see the potential. I'm not really sure. But I think HeartVista does this in a very smart way by getting FDA approval. So basically, everybody can install this, and then it opens a gateway. There's other vendor-neutral approaches. So there's GammaStar and PulseSeq, and actually we're working together. The MRI Fair idea is the three of us, the three groups that do vendor-neutral MRI, joining forces and saying we should present a unified front. And I think vendors are letting us do our thing, partly because it's very few people doing it. But for example, we have it installed here at the Heart Institute. There's a GE and a Siemens installed at the Sunnybrook in Toronto. If anybody here in Montreal is interested in getting a license and trying to install this on your own system, we actually do have some licenses, and it would not require purchasing RT-Hawk. So I feel that until there's a critical mass of people using this, vendors are just going to let us slide. And if they start complaining, honestly, that's a problem I want to have. So let's just see how they respond. I think they're going to be cooperative because they recognize that there is potential here.
Thank you. I'm going to try to activate the sound for someone who raised.
I see Walt Schneider raise a hand. Yeah.
You should be able to go ahead.
Okay, can I talk? Can you hear me?
Yes.
Okay. As a comment, I too have been in the fight for quantitative imaging for, I guess, a decade. Our approach is different. We got the VA, which is the biggest customer in the world, to say we want to be there in 3 years. And we are rolling out to 119 VA centers a common phantom for both the NIST part and anisotropic diffusion. Short story, we took a Siemens 3T version 11E and 11D and took the same pulse sequence and got a non-linear function on T2 star depending on one of the filter parameters. And if you try and match parameters by matching the peripherals, there are 58 parameters in the Siemens sequence. It's whack-a-mole. It can't be done, but you can see it and figure out how to fix it. My approach to the vendors is to say every quarter we are going to publish from 500 magnets. This is your match to a linear line for each of the metrics. I did a review for how did we actually get normalization in blood biomarkers. There are 6,000 labs that reproduce within 2%. It took 30 years. And in CT, which is quantitative, it's been 38 years. We haven't done it in MR. And for those who are interested, I'll put my email in the list and I can send you a copy of the paper that reviews how it succeeded in CT and MR. And the answer is, in blood markers and MR is, it became a scientific proposal from the scientific community, and then Medicare said, we won't pay you. That's the path we are on, using the VA install base of 500 magnets to get there. And anybody who's interested, I'll send you a copy of the paper.
So first, well, thank you very much for chiming in. And I'm aware of your efforts, and I know that they are really impressive in the scope. I also think that this approach can pay in dividends. There are success stories with T2 star and thalassemia, for example. It requires very careful coordination and very careful calibration of lots of scanners with the same sequence, the same phantoms. And actually in thalassemia, you do have some thresholds for T2 star that determines whether you give chelating agents. So there are few success stories in quantitative MRI, and I think we need to focus on those before generalizing.
Thank you.